Example number 2 for the shear and moment diagram. Example 2. So also a simple supported beam here, and we also have a pins on the left and the roller on the right. Instead of concentrated load in the first example, this second example, I assume that is distributed load, uniform distributed load throughout the beam, and assume that it's 50 pound per foot, and the distance, the beam span equal to 10 feet. And then we can draw, hopefully now you master and draw a little bit faster for shear and moment diagram. So here we have for the shear and the moment diagram we have here. And we can have the right side, and no change between the right from left to right, so we don't need to have the middle point that we have in the first example when you have 10 pounds in the middle. So what do you have? So V, and again that it will be pounds based on the problems, and positive, negative, and then you have moment, foot pound for this problem, and positive, negative. And we now apply the node, but always first find out the external reactions at the support. You see 50 pounds for 10 pounds, so equivalent 500 pounds in the middle of the beam, so 500, and in the middle, so that one is 250. Of course you can go ahead to find out with the equilibrium equation, but that simple enough. By now you can be able to know that 250 pounds. So with that, we draw the shear diagram on way first and start from left to right and start with the 0, and you recall. So let's start with the 0. Always from the left is 0. And then 250 pounds going up, the change, it called the 250 pounds up. It's called the discontinuity in the shear. Move up 250 pounds, and now you already know, so move up. And that one is plus 250 pounds with the units. And then from left to right, the change in the shear, area under the load curve, the change in shear area under the load curve, and the slope of the shear diagram equal to the magnitude of the load. The magnitude of the load in this case 50 pound per foot, 50 pound per foot. And area under the load curve here, as you can see, 50 times 10. So the area under the load curve there, you can write down equal to 500. Right? Area under the load curve. 50 times 10, 500. And that equal to the change in the shear from left to right. So left is plus 250 at that point. You can see that. At that point, on the left is 250. 500, and in this case, the load going down, so that 500 is negative. But positive of the W is move up. And you can see here, cause continuity change in the internal shear and angle up, right? And in this case, going down, the load going down, so angle down. So that's what you have, and the magnitude 50 pounds, so that is slope from plus 250 plus negative 500. That change it become to the right side, negative 250. Because that change from left to right equal to 500. So that start at the 250. It will get 0 in the middle. And then get negative 50 on down at the right side. So that will be 500 pound change from left to right. And then at the right side, we have 250 pound going up. So it creates a discontinuity in the Shear diagram. Move up. So from negative 250, 250 going up. Move up 250. And that stop at exactly 0. So that I say always start at 0 from left. Go continuously to the right. And then stop at 0. And as you can see, go back to the distributed load here for the designer side convention. As you can see, go up here. That's what they say. Cause a continual change in the internal shear and go up if the W going up, right? In this case, the example number 2 cause the discontinuity continual change, and in this case angle down because the W going down. Okay, so that is the Shear diagram. Now go to moment diagram. Like I said, it always look at the shear moment diagram, look at the Shear diagram, and first it always find out the areas under the shear curve. So that areas from the middle, as you can see, this will be 5 feet. This will be 5 feet in the middle there. Of course, 250 negative 250, the intersection here have to be in the middle. So that is the triangles there. Triangles 250 times 5 divided by 2, it will be 625. 625. And on top, so it will be positive. That is the areas from left to the middle. And exactly the same, but it's negative 625. 625. So from that, you have the change in moment equal to the area under the shear curve. So we have that because that is the critical point there. Then always start with 0. Always start 0 from the left. And between that left to the middle point. Middle point. Let me put that in blue. Blue there. So that with blue. Blue there. 0. Change moment from left to the middle equal to 625. So there are a few ways that you can draw, right? Okay, so let here from 0. So that somewhere that point, it have to be plus 625 to make the change from left to the middle equal to the area under the shear curve, which is 625 foot-pounds. So you have this is W distributed load W, and you can see there uniform, then straight line on the V, and then when it's uniform W, then the moment it have to be parabola. So double. So with that, how can I draw parabola? So a curve, right? We can draw which way I go. Let me draw it. Can I draw that way? Can I draw all the other way? Right? So there is 2 ways to draw it to make the parabola. Right? So let focus one. If I draw that, then you have here, you have one here. That point for the shear, it equals 0. And the shear at that point equals 0. If you call the note for the moment, slope of the moment diagram equal to the magnitude of the shear. So the slope at that point in the middle for the moment have to be zero. But if you draw that way, it's not zero, because the slope is zero when the tangential line on that point to the moment diagram have to be horizontal. So with that, the only way that you draw for the parabola here, and that tangential line, it will be horizontal. It's zero. So as you can see there. So that I have to erase that. And then negative 625. So from positive 625, negative 625. Then you also have draw the same parabola and go to zero to the right, and that is the moment that we have. Right? So that start at 0 plus 625, and as you can see here, the slope at that point in the middle is horizontal. That way is correct for that way you draw the parabola, because the shear at the middle point in the shear diagram equal to 0. Then slope have to be at that point have to be 0, because we talk the slope of moment diagram equal to the magnitude of the shear at any point, including the middle point in there. So 25 foot-pounds, that is the maximum moment. And now go to the what is like I'm talking. As you can see, for the shear that I draw there is it look like not straight, but at that it's actually straight line. So you put the S so that you don't call, oh, you're drawing a curve or straight line. And then the second for the moment diagram, of course, that it will be parabola. And this is parabola. So every segment you have to put what line you have, and that I show you how to draw it correctly for this example number 2. And when you look at it, makes sense, the maximum moment in the middle, because that with that beam it will tend to be deflect out, and a positive moment, it makes sense because if, with that distributed load applied throughout the beam, it creates the tension throughout the beam in the bottom and compression throughout the beam on the top. And with that, the moment it will be positive, and that reflect in the diagram. Why positive? If you recall the internal moment convention in here for internal forces moment, positive when creates a positive or tension at the bottom, and compression at the top, that is positive moment. And with that, we also know, oh, the maximum moment in the middle. So with that, we finish for exam 2. We have 2 more examples, by the way, to investigate other